Okay, on this example number 4, what we have here is a 212 kg slender rod is pinned to a small roller A. Okay, it is pinned here, and this particular slender rod is slide freely along this particular slot, so it can move left and right. Okay, if the rod is released from rest at theta equal to 0 degrees, which means initially it is here, okay, and then after the release, of course, it will go downwards, okay, like so. It will rotate, and the point of rotation is A here. Okay, now we need to determine the angular acceleration of the rod and the acceleration of the roller immediately after the release. So remember that it starts from rest. Okay, to begin with, we must know that this particular slender rod is uniform in the sense that the point G normally that we put is somewhere here because it is uniform, and the total length is 0.6. Therefore, from this point A to point G is the same, should be the same from point G here, sorry, to this N here. Okay, here it is 0.3. Let me remove this one. Okay, it is G 0.3, and here also 0.3. Okay, now this is our point G. Remove it. Point G should be in the middle here, somewhere here. It is our point G. Okay. Initially, yes, you can look into the summation of force in the x direction, and it is going to end like this. Okay, which means that the because initially it is at rest at theta equal to 0, so it is like this. So at that particular instant, there is no forces in the x direction. Okay, there are forces involved in the y direction where there is a mass acting at this point G here. Okay, there is a W here, but in the x direction, nothing is there. So that's why you get a AG in the x direction is equal to 0. Okay, now we look into the summation of moment at point A. And then counterclockwise motion is our positive direction. And again, this one is on the right hand side, we have this part here is MAG times R, and then plus I alpha, IG alpha. So in here is our I, 1 over 12 M R square, okay, times alpha. That this here is M, 1 over 12. And this part here is the MAG in the y direction, because we know that AG in the x direction is equal to 0. So this is AG in the y direction, because the forces or W here, this is representing the forces in this particular direction. So it creates clockwise motion. Okay, and then um, times the 0.3. And on the left hand side, what we have is the forces that causing this motion. Okay, which we have mg. Okay, because initially it is like that, and the w is acting downwards like that, and the perpendicular distance from the point A here is 0.3, and then we multiply by 0.3 minus because of clockwise motion. And here what we have is uh, the first, rearrange this particular question, simplified, then we will get this, the first question, and then we know that it start from rest. Okay, so omega is equal to 0. Okay, now you can refer to the previous notes or previous examples. We want to calculate the acceleration of point G relative to point A. Point G, okay, here we are referring to point A. Okay, point G here, AG is equal to AA, okay, this one. The absolute acceleration at G is equal to absolute acceleration of point A plus alpha. Alpha is the angular acceleration of this particular rod. And then cross with RGA. RGA is from here to here. Okay, RGA. Okay, and then minus omega square, because this particular problem is a 2D problem, and we can simplify into this equation. Okay, omega square dot product with RG slash A. Okay, now we can plug in all the values that we have. Here what we got is, of course, in the for AG, we only have expression in the y direction as what we have obtained just now, because we already proved that AG in the acceleration is equal to 0. So we only left with in the j direction. And then uh, uh, this AAI, okay, AA is the extraction of point A, okay, point A shall move to the right. Okay, we assume that uh, this is our axis of reference axis. Okay, anyway, and AA is going to the right plus minus alpha k, because we know that this rod will move counter clockwise motion, and this point k is going out from this particular page. Then cross with the RGA, we know that it is 0.3i. Okay, RGA, A is here, G is here. Okay, RGA is that one, and it is 0.3 I lah. Okay, and minus omega square RG with respect to point A, and we know that omega is 0, so 0 square multiplied by RGA, then it becomes 0. So we can obtain this expression here. Then we can look into the the I component as well as the j component of it. Okay, in the I component it is, and it is the j component. And now we know that AA is equal to 0. Okay, and then AGY is equal to minus 0.3 alpha, and this is our second equation. So now we can solve these particular problems because we have two equations, and then we want to determine two unknowns. So this our alpha, which is 24.5 radian per second square, and the acceleration of point G uh, is equal to minus 7.36 meter per second square. Okay, and it is going down. Sorry, our axis of rotation is reverse. That should be like this. Okay, sorry for this error. Okay, thank you.